Okay, so the main difference between the collocation and the shooting method is the way it handles the dynamics. So they differ in how they handle the dynamics. Okay. So what collocation method does, it actually opens up the dynamics in the sense you need the equations, and we'll basically try to ensure that those equations are satisfied at discrete points. So collocation method will discretize the equations of motion. So that is, in this case, the equations of motion are x1 dot equals x2 and x2 dot equals u. What it effectively does is, if you have x1, x2, and u, and let's say that this is time, you will choose a set of points till, say, time t. For each of these x1, x2, x3, it will basically find values at each instant of time. So let's say this is x1. They'll do the same thing for x2. x2, and then same thing for u. Okay, so if there are, let's say n, these are called grid points, then because we need to find the value at each grid points, there would be n points for x1, n points for u, n points for x2. So we'll end up with 3n unknowns. Okay, and that's how it proceeds. So let's see. So that's just the idea of what it does. Let's now try to break this down, this formulation which we have. So we need to take this, combine with this idea that collocation basically discretizes the space, and then try to write down a set of equations. Okay, so in any optimization problem, there are three things you need to specify: the variables. So these are the variables, a cost. This is the cost, and then the constraints, which are over here. Okay, any problem. Now, when we define the variables, cost, and constraints, we want to write them in terms of the unknowns. Here, there are 3n minus 1 unknowns for x1, x2, and u. And then there's going to be an unknown here. This is also going to be an unknown, right? Because we said, if you see here, formulation, t and u were unknown. Well, in this case, we have more unknowns. Besides u, we also have x1, x2. So let's write down those three things: optimization variables, cost, and constraints. So the first thing is optimization variables. So it's going to be time. There will be u, I. Here we'll assume that. Okay, so the way I chose this is because because the way Python is set up, it starts indexing from 0. I just chose to start from 0 and then go to n instead of saying n minus 1. So this actually causes it to have n plus 1, not n, right? Because there's a 0. So I wrote down here n, but really I'm going to start using n plus 1 just because the way Python is set up. If I was using MATLAB, maybe I would have gone from 1 through n. So let's say n plus 1. So n plus 1 for ui. Then I said there would be the position. So that would be, well, this is the way to do it. Oh, I see. I know why I did I. Because of this 1 becomes hard to write it down. So all of these are n plus 1. And then there's 1 over here. So if you ask me how many unknown or variables are there, how many things, how many parameters you can tune, it's going to be 3n plus 4. And the choice will depend on n. N is something which you choose. The finer the grid size, the finer the grid, or the more the number of points, the better is your solution. So the next part, B, is the cost. And that's kind of obvious. It's just minimize the time. C is constraints. So we take everything over here in the formulation which we had and write it down as a constraint. So we need to write equality, inequality, and so on. So in this case, let's see. So we have the dynamics. Let's write that down first. So if you have x1 dot equals x2, we have to discretize it because we only accept values now at these discrete points. So the easiest way to do that is to use Euler's method. So we have x, this is x1 t plus delta t minus x of t divided by delta t equals x2 of t, right? Other way of writing this is x, you can write this as x1 I plus 1 because I'm dealing with I equals 1 through n minus x I equals x2 I delta t. In other words, x1 I plus 1 should be x1 1 I equals, okay. So xi plus 1 minus x1 I minus x2 I delta t equals 0. So I always try to write as an equal to 0, right? So this is going to be the equation. And this equation is going to be true for I equals 0, I equals 1, and so on till I equals n minus 1. Because when you put n minus 1, you get I plus 1 becomes n minus 1 plus 1 will be n. So this is true for I goes from, in blue, 0 to n minus 1. So these are going to be, you can just count, these are n constraints. They're actually linear constraints, right? Because n plus minus 1 plus 1, there's 0. Okay, similarly, I can write an equation for x2 dot equals u. It will be a very similar form. So let me write that down next. So the next one is x2 dot equals u. If I write down the Taylor series expansion, I get x2I plus 1 minus x2I minus delta t ui equals 0. And then I just do this again for I equals 0 to n minus 1. So these are n constraints. Okay, so I've knocked off this one and this one. This one is going to be a bound, so I don't worry too much about it. This one is also a bound, so I just specify it to be minus 5 and 5. Each of those should be between minus 5 and 5. So let me not specify that, but let's do the equality constraint. So this one, these four would be as follows. We have x1 at I equals 0 is equal to, that's the first grid point, should be 0. X1 at the last grid point should be d. The velocity at the first grid point should be 0. Velocity at the last grid point should be 0. And these are only four. Okay, so how many constraints do we have? Number of constraints. So I said we have here n constraints for the first equation, n constraints for the second equation, and 4. So that answer is 2n plus 4. Okay, so what we've done here is written down the three things we're interested in, variables, cost, and constraints. Now, here's the thing to think about. We have some numbers we can tune. The optimization is free to tune. These are 3n plus 4, right? We can choose t, we can choose u, x1, x2. We can choose okay, we can choose 3n plus 4 variables, but we only have 2n plus 4 constraints. So let me write that down. So optimization variables are 3n plus 4. Constraints are only 2n plus 4. Okay, so think of constraints as something to do with equations, something which needs to be satisfied. Variables as something we can tune. So the free variables are going to be simply 3n plus 4 minus 2n plus 4, which is n. So there are n free variables. Okay, what this means, normally when you solve problems in maybe other classes, you'll have n equations, n variables. So when you have n equations and n variables, you can solve for each of those values uniquely. And sometimes there's no solution, but let's take the case when there's a solution. So if you have ax equals b, normally you can solve for x because x has dimension of n, and then ax equals b, there are n, a is n cross n, b is n cross 1. So you can solve it. The thing about optimization is usually you'll have more variables to tune, but only fewer constraints. So here we have n extra variables. So we can tune these extra variables, which means that there's going to be more than one solution. If you have n equations and unknowns, there's only one solution. If you have more, if you add just one more variable to that, so let's say that there are n plus 1 variables and n constraints, you have one extra variable, but that leads to infinitely many combinations because of that extra variable. Here you have not one, but n free variables. So you have a whole lot of control over what you can do. So all the optimization problems will have this thing, which is there are lots of decisions you can make, lots of combinations you can do, and only some of them will give you, or actually, if the optimization is good, only one of them will give you the best solution. Okay, everything else you try will not give you a best solution. So by setting it up as an optimization problem, you are actually biasing it to give you the best outcome for that particular cost function. So there are infinite solutions. Yeah.
We have 3n plus 4, right? Else we wouldn't have got that 3n plus 4 because it's n plus 1 every time.
It depends. I set this up from 0 to n. If you set it up as 1 to n in MATLAB, you'll have n conditions, and then it'll be, instead of 3n plus 4, it'll be 3n plus 1. But you could also set it from 0 to n plus 1. N is just a number. I sometimes set it up 0 to n plus 1 to n plus 1 in MATLAB, but it's totally up to you. N can be anything. Doesn't really matter. Just that you cannot have a zero index in MATLAB. That's the thing. You cannot put u of 0. It'll fail.
N number, like constraints and this will be equal.
Yeah, so it'll all scale with that, right? Okay, so there are infinitely many solutions, but the optimization will bias it to a single unique or a single solution. Because anything else you do with those variables, you will not be able to achieve optimum. Okay, so now that we have set it up, okay, so you have this. You can look at what we did with numerical uh, optimization. If you can put it in this form, right? If you can write it in this form, then you can, of course, write it in SciPy optimized. You need bounds, you need constraints, and you need the cost. Okay, and they should be discrete equations. You can do the same thing here. Now that we have specified this, we have the optimization variables, which are right here. We have the cost, and we have the 3n plus 4 constraints. So it's all ready for implementing in SciPy optimize. So what I'll do here is I coded it here. It's fairly long, 140 lines, and I just have plots. I don't do animation. Before I get into the code, we know that the intuition that the solution is that you get full throttle and then you brake full brake. So let's see if it gives that. I think we'll put a timer here. Oh, 10 seconds. Okay. So it's still computing. Okay, here is the solution. X dot, and U. Okay, and then it takes about, looks like, we turn this off so we can look at it. Okay. It's printing position, and then let me print the time it takes, which is t. Okay, let's print it again. So now it will not close the window. Okay, so before it does that, so here is the time. It's 2.23. Okay, so it says that you need to stop in 2.23 seconds. That's the first thing. Second thing is, let's look at the profiles. The first one is the position. So it starts at 0, and I think I made the, so it ends at 2.23, by the way. So that's what the time is. And then it should end at, I think I specified the distance to be 5 meters, so it's 5. Okay, x dot is the velocity, which I think we get more intuition from u. So u is what, here's what we do. We start at -5. Well, we start at, this is strange, right? It starts at -5 and goes full throttle 5, keeps it at 5, then goes all the way down, decelerates, and turns down. So what's going on here is not clear. I would have expected it to be fully positive. Why would it go negative? It go +5 and keep doing that, and then go to, then sort of have a flat piece here and then go vertically down and to -5 for the rest of the time. So this is a problem which happens because of the discretization. If I increase the grid size, you can see that there's 1 point here, 1 point here. It will actually become more and more like the one which we expect it to be. So we can actually check that. Let me close this. Look at what the capital N is. So I specified N to be 10 grid points, but let's make it, let's say 20. And it'll take a little bit more time because it's pretty fast. So now you can see, look at the control. It goes from -5 to 5, but then that's much more vertical, and then it goes negative, positive, sorry, negative, that is breaking and stays there. Okay. Okay, so this is actually something which which should go away. It should actually start at +5. This is just the something which happens because of the way it's just a problem with the optimizer when you have you don't have a fine enough grid size. That's my guess. Let's try this, and let's go to now double this 40 and see if that goes away. Okay, so it's becoming more vertical. Should have started from 5 and shouldn't have this, and then it goes down. Okay, let's try. Let's try 100. I think if you try to increase the tolerance on this, it might actually give you, it won't give the -5. It's just a discretization problem. So now it's taking a lot more time because I've specified n equals 100. Remember, n equals 100 means there are 3n plus 4, 300 plus 4, 304 decision variables. That's a huge number of things to tune, and that's why it takes more time. 40 was just very quick, but 100 takes a lot of time. Maybe it will not converge. So it took a while, but then gave this. So you can see the solution is actually going to ramp up, ramp down. It shouldn't have done -5. It's like starts off with breaking and doesn't have to do that. I think there's a problem which is because of the discretization. Okay, so that sort of agrees with our intuition. That's the strategy to follow. Let's look at the code. I'll do that fairly quickly. The way to do this is to actually start from the call to the minimize. So there should be a cost. That should just be the time. You need to give the method. I use sequential quadratic programming. I need to give the constraints. I need to specify our tolerance, maximum iterations, and so on. Okay, so there is bounds, there's constraints, and then there is a cost. We can go through all these. So cost is just the first variable. So I specified the optimization variable starting with time to be for the first index, so x of 0. Then I have the nonlinear functions. I actually put down all the equations of motion. You can see this position, velocity, u as the nonlinear functions. So what I do is I find the position minus position. So this is basically Euler's method. And this is basically something which needs to go to 0. So what I do is I set it as defect. Defect means that defect is the difference between what I would get at ith step by doing this integration minus what I would get without for the next time step. And that difference better be equal to 0. And so this tries to get this to 0. Same for velocity, the equations of motion. And then these are the 4 equations for the position at time t equals 0, position at time t equals, in this case, n is d, velocity at the start is 0, velocity at the end is 0. So all these equations are written down such that you get a 0. So I return c equal to, so this is basically the first 4, and then these are n plus 1, n plus 1. So it is c equal to, which is passed back. Then we have, so that's cost parameters. I'm trying to get to the bounds. Tmin, Tmax. Okay, so this is just specifying all the way to interpret this is this one. So x0 is the decision variables. How many optimization variables? Maybe I should just write it as a comment. Optimization variables. So this, I just wrote it down this way so that it's easy to understand. I said there's 1 for the time, that's the first one, n plus 1 for the position, n plus 1 for the velocity, which is the next one, and n plus 1 for the control, that's the next one. I need to specify a minimum, the min and max. So what I do is I initialize it with 0. I initialize so x is the decision variables, but they have bounds. You have to give them the lower bound, upper bound. So I specify 0, but then I change them. So the 0th one is t min, t max. I just specified some numbers 0 and 5. You could make it 1,000, but what happens if you give it 1,000? It'll actually try to search over that range. It'll slow down the optimization. And then I give the bounds for the position, bounds for the velocity, and hopefully it's easy to understand. So these bounds become the limits. And then we have the optimization. Okay, so this basically is how you set up an optimization problem. You convert something which is continuous time, has infinite values, to finite values.